Hello everyone. So today we will be talking about a special topic which is a continuation from the units and dimensions that we discussed in the last lecture, and this is about error analysis and a very fundamental concept when we are trying to solve problems and seeing what exactly our measurements lead to. So to start with, let's start with the definition of error analysis, and we see that it is the process of determining how accurate and precise a measurement is. And you can see that I've highlighted two words in this definition, which clearly is quite ambiguous if you see it in your day-to-day lives, that we use accurate and precise almost interchangeably. However, there is a thin line of difference that separates the two and classifies it into two different meanings. So what does accuracy mean? It means that it defines so accuracy defines how close a measurement is to the true value. So I'm highlighting the word how close because it is used to see or used to compare, in fact, two values, and you can see how close they are to the real deal. So that's what accuracy is. Whereas precision or precise means how consistent a measurement is when it is repeated. So when we're trying to do an experiment, we see that often most of our results come within a certain range of values which are very close to each other, and then we say that these are precise. And when we see that the experiment that we are trying to perform is giving us results which are not so accurate to the real value but lie close within that that measurement that we are trying to take, falls within that metric, in that case we say that it is accurate. So for example, let us take a case when we are testing a 50-gram sample, and the first test gives us a result of 47.5, 47.6, 47.5, 47.7. In this case, you see that the values are really close to each other, right? So we get values which are almost the same and differ only very slightly. However, it's divergent from the real value, which is 50 grams. So it's pretty far from this value, which is 50 grams. In that case, we say that test 1 is precise because it gives really close values no matter how many times the test is repeated, but not accurate. Why? Because we are not even close enough to the real value, which is 50 grams, right? In the test 2, we see that, and that's the second case, that we see that the values are really close enough to 50 and they lie significantly near to that range, where the first one is 49.8 and 50.5, 51.0, 49.6. However, when we compare values 49.6 with 51.0, you see that the difference is greater than 1. However, it's nearer, it's closer to the real value, which is 50. So it's closer to 50. However, the values are not well finished. It means that the result is accurate but not precise. So this is the fundamental difference between accuracy and precision, and I hope through this example you can understand how to distinguish between the two when you're carrying out an experiment. Next up is significant figures. So the ideal concept of significant figures is how many digits in a particular experiment that you get do you have confidence in, right? So let's say if you're measuring anything, a physical quantity, let's say, that can be anything: force, displacement, torque, work, anything like that, which tells the number of digits in which you have confidence in. That means you are certain that if I'm considering that many number of digits, I'm pretty sure that my calculation or my measurement will give fruitful results. And obviously, when we say that you have more number of digits, so it means that you have better accuracy. If you remember in the definition of in the way light is measured, the SI unit of light, SI unit of time, is measured. You see that it is measured in terms of wavelength of light, which has a really long number. So it has at least 9 to 10 significant digits. It means that it is very accurate because you cannot compromise when it comes to comparing standards, right? So you can say that it is more accurate. Okay, So when you consider significant figures, and that is very important when you're trying to solve problems again, there are certain rules, and I'll discuss them one by one. So the first one is all non-zero digits are significant, which means that, let's say if you write a number even with a decimal place, no matter what the number is, as many digits are there, it's significant. So first example, you have 3, second you have 4, third you have 5, and that is pretty straightforward. Okay. The second rule states that a 0 becomes significant if it appears between two non-zero digits, and that is again a very self-explanatory. It means that, let's say if you have two non-zero digits and if you have a 0 in between, that is also counted as a significant digits, as you see in the examples below. This is for 3 significant digits, this is for 4, and this is again 4 because you have two zeros. However, it doesn't matter because the zeros are within two non-zero digits. So this is the second rule, and these things become very important when you are trying to analyze between two measurements that you have taken from an experiment. Rule number 3 states that, let's say zeros in front of a physical number or of a number, or placed to the left of a number, are never significant. So this is a very crucial point to consider, because let's say if you have a number which is 0.543, then it has 3 significant digits. It counts 1, 2, 3. These are the 3 that it counts. Let's say if you have a number which is of this form, and then it counts 2 significant digits, and if you have a number of this form, it counts only 1. So the zeros which are placed at the left of a number, all of them are insignificant. And this is a very critical step that you need to consider, because you will see that there are very close approximations to this particular rule. There are rules which are pretty much similar, but they are actually not the same. Okay, let's go to rule number 4, and it says that zeros to the right or trailing zeros are always significant, and you need to know the difference between point number 3 and point number 4. The one is on left, it's never significant. The one on the right is very significant, it's always significant. So as you can see that there are 3 non-zero digits and 1 zero digits. However, all of them are counted. So it has 4, the next one has 5, the one after that has 6, because there are 3 zeros after 3 non-zero digits. So these are specific rules of significant figures, and I'm emphasizing on them because each one of them carries their own meaning, right? So one of the most interesting facts about this significant figures lies in the exponential notation, because here you might want to consider it differently. So, and this also simplifies the problem to a great extent. So let's say if you're writing something in exponential notation, the numerical portion gives the number of significant figures, which is trying to say that only the numerical portion matters. Only this matters and nothing else. The zeros don't matter at all. That means the 10 to the power something, that doesn't matter at all. So let's say if you have this figure 1.75 10 to the power minus 2, that has 3 significant figures. Again, if it has 2.95 10 to the power 5, has 3 significant figures again. However, if you had written it in terms of, let's say, 295 and then 5 zeros after that, or multiplied it with 10 to the power 5, you would have got a different result. But in exponential notation, this thing is allowed, and you can definitely write it in terms of this one. And you will see when you're doing numericals that this kind of notation is most prevalent in most of science and engineering, right? So this is all about significant figures that we see when you're trying to get a result from an experiment, or you're trying to solve a problem. Mostly you might have to face a situation where you will have to make a choice between how many digits would you consider for your next step, and that is when significant figures come to play a very important role. So you have point number 1, 2, 3, 4, 5, and these 5 rules are the cornerstone of significant figures. Coming on to the next topic is rounding off, and as you well know from your childhood, rounding off describes certain rules, and these are pretty important when you are trying to solve a problem which relies much on lower number of digits than the one that you're working on. So let's say if the digit, and that's the first rule, if the digit to be dropped is less than 5, then the preceding digit is left unchanged, as you might see. So 7.82 is rounded off to 7.8, because the 2 is not 5 and less than 5, of course, so it's dropped off. Again, 3.94 is dropped to 3.9. Sometimes these systems are also used in grade calculations, as some of you might know. Okay. The next point is, if the digit to be dropped is more than 5, then the preceding digit is raised by 1, and that's a very common notation. If it's 6.87, it's raised to 6.9. If it's 12.7, it is raised to 12.8, and so on. It's pretty trivial and very self-explanatory. And these rules are something which is mostly used in practice, and that is point number 2 for our case. For point number 3, we have, if the digit to be dropped is 5, let's say, and followed by a digit which is not 0, then the preceding digit is raised by 1, right? So let's say if 16.351, and this is what I'm trying to consider, then it is rounded off to 16.4. It's as simple as that. Again, if it is 6.859, let's say, and you have 5 over here and you have 8 over here, it's simply rounded off to 6.9. That simplifies your calculation a lot. You will see that you will need it at times when you're calculating g, acceleration due to gravity, when you're solving problems. You see that this is a very important artifact which comes about at times at hand. So it's very handy at times, right? The point number 4 is very interesting, because it says that, let's say if a digit is dropped by 5 and or 5 followed by zeros, so let's say there is a 0 after 5, and the preceding digit is left unchanged if it is even, right? So let's say if it's 3.250 and we see that 6 is even, so 5 is dropped, 0 is dropped, and the final result is just this 2, right? That's what we have. Again, let's say if our digit is 12.650, I'm sorry, in that case it becomes 12.6, right? 5 and 0 is dropped. So if there is a 0 after 5, it is dropped, and if the number which is preceding 5 is even, in that case it stays even. However, the case is opposite, as I have stated in point 5. If the digit to be dropped is 5 or 5 followed by zeros, the preceding digit is raised by 1 if it is odd, and that's a very important step. If it is odd, it's raised by 1. So as an example, 3.750 becomes 3.8, right? 3.750 becomes 3.8, okay? And then let's say if I have this number, it becomes, as obvious, 16.2. 5 and 0 are dropped, 5 and 0 are dropped, and you only have certain values. So these kind of significant figures often become very important when you're trying to solve problems that have very close options to consider, and you will find it important, like you will find it useful if you're thinking intuitively as well, right? There is a thumb rule for significant figures. I would sort of call it as thumb rule, because it's very important when you are trying to figure out which is more important between two results. So the final result cannot be more precise than the least precise measurement. So let's say if you're doing a series of experiments, and then in one of the steps you get a result which has lower precision than all of the steps. In that case, your final result will depend on the step which has lower precision. I repeat, let's say if you're doing a series of experiments and you have a step which has lesser number of digits in consideration compared to other steps, or is less precise than all of the steps, then your final result will depend on this least precise step. So this is exactly what a thumb rule of significant figures is. When you are in upper standards, you will learn something known as the rate dependent step in chemistry. The concept is similar, that the rate of the reaction depends on the slowest, or the rate which is the slowest of the slowest of all the steps in the reaction chain, right? The slowest one really controls the entire step. So that's exactly the idea behind the least precise measurement. Okay, let's go rule by rule. So this is the first one, and it says that the result of an addition or subtraction of a number having different decimal places, which is essentially least precise measurement, gives a result with the least decimal place. Confusing, right? I'll just simplify it. Okay, so let's say I have a figure, I have 33.3. okay, so after decimal I have one figure. Let's say I'm measuring this thing with a ruler. Easy, right? Okay, so let's say I have got this value using a ruler. Let's say I have got this value using a vernier caliper. Okay, and let's hope I have got this value using a screw gauge, right? So your final result will be something of this form. Now, according to what we have read so far about significant figures, if you see the steps, then you see that this follows exactly point number 1, and it reduces to 36.7 because after decimal, I'll only have, and I should have, just one decimal, right? Because this is the rate determining step. 33.3 is the least precise measurements of all the three, and this is what will control the final result. Okay, so think about point number 1. Think, why should I use this? My understanding is because if you are measuring something with a ruler, it's big enough to not consider fine measurements such as screw gauge or vernier caliper. This is my intuitive understanding of the problem, but this is a general rule of significant figures when you're doing a certain set of experiments one by one or one after the other, right? Second step says that for multiplication or division, answer rounded off to same number of significant figures. I repeat, for multiplication or division, answer rounded off to same number of significant figures as possessed by the least precise term. Again, that's an iteration of what we said in our thumb rule, that when you're doing a multiplication or division, instead of going into a number of digits after decimal place, we see how precise one measurement is, right? So when you are multiplying, let's say this is a figure which has 5 significant figures, and this has 2 significant figures. The zeros ahead does not count according to point 2, and this counts because 0 in between 2 non-significant digits counts. So this is 5 significant figures, this is 2 significant figures. So if I multiply, I get a value like this. You see that it has 1, 2, 3, 4, 5, 6 significant figures, right? But we cannot do that. We have stated that we need to have as many digits as the least precise measurement allows, and that is 33, and that is rounded off based on, again, rounding off point number 1. If it has 32.6, I just increase it by one value, which is 33, and that is the final value of the measurement. Okay, let's take a minute break and reflect on what we have done so far. We've studied about significant figures. We have studied rounding off. We have studied how the rules matter if you have zeros in between two non-significant, between two non-zero numbers, and how does significant figures play a role in measurement and other artifacts of error analysis, right? So you can reflect on these things as you go forward. So let's start with the final module, which is the errors in measurement. So while you're doing a set of experiments, a lot of errors can creep in because of a number of sources, maybe due to machine error, maybe due to human error, maybe due to the fact that you are in an environment where G is not equal to 9.81, let's say. Maybe the standard temperature, the pressure of the room might be different than the one that you're trying to measure in. So it might have a lot of difficulties in measuring, and it might not be exact. So absolute errors, so there are few different types of errors that we'll discuss. First one is absolute error. It is the magnitude of the difference between, and let's note it word by word, it's the magnitude of the difference between true value and the measured value, right? So let's say we have n set of values, n set of measured values, which is numbered from a1, a2, a3 till an, and then add them up and divide by n. So am is the mean, algebraic mean of or the arithmetic mean, to be precise, of the set of values that I've measured. So delta a1 is the difference between this mean value and the first recorded value. Delta a2 is the difference between the mean value and the second recorded value, right? So this is the absolute value. This is the absolute error. So let's say for a1, the absolute error is delta a1. For a2, absolute error is delta a2. So this is how we distinguish between different kinds of absolute errors. And similarly for delta an, it's am minus an. right? So there will be as many number of absolute errors as there are measured values, right? The most important thing to consider in this statement is that absolute errors may be positive or negative. Just because the word absolute means an absolute quantity doesn't really imply that for errors. It can be positive or that can be negative. Okay. And then we have a mean absolute error, which takes into account all the absolute errors, adds them, and divides by n. But in this case, however, we take the modulus of the absolute errors, because just as I said, the word absolute doesn't really imply only the magnitude of the particular error. So that's why we have to enforce a modulus operator, and we add them up and divide by n, and that gives us the mean absolute error, the mean value of the absolute error, right? So if you want to find out what is the final result of something which has been measured, so first of all you have a1, a2, a3 up to an, and then step 2 you get something which is called m, and then you get delta a1, delta a2 up to delta an. Step 4 you have something which is called delta a bar, which is the mean of the absolute errors, and then you finally have your final value, which is a, and a has this formula, which is am plus minus of delta a bar. Now it depends on how your problem is. So this is basically an error bar. So this is sort of the accepted value of a that you get. So it may be positive or it may be negative. So it doesn't matter because your measurement can have either directions. So that's the final value of the measurement. Relative error is pretty simple, which is point number 3 in this case. So that is the ratio of the mean absolute error with the mean value. Okay, and that is very simple. This is just for purpose of your numericals when you're doing them. And then you have percentage error. Percentage error is simply the relative error multiplied with 100. So that will give you a percentage of how much your error is, right? And the final topic for the day is how propagation of errors count. So let's say if you're adding two numbers, and let's say if both of the numbers have some error within them, and then how does the final value get affected? So what is how much error creeps in when you add two values which has certain inherent errors lying within them? So let's say if a has an error, b has an error, then how much error will x contain, right? So delta a is the absolute error while measuring a, delta b is the absolute error while measuring b, and then delta x is the same, right? So the maximum absolute error is given as delta x is equal to plus minus of delta a plus delta b, because it can have both negative and positive signs in either case, right? The percentage error says that let's say if you take the value of the sum of the absolute errors and then divide by the values which I have given as input and then multiplied with 100%, and that will give you the error in sum, right? Exactly the same lies for error in difference. It's just that the denominator changes to a minus b, because a minus b is the input which we are giving, and let's say that this is our input because this is what we are giving, right? So we are trying to add two numbers. So this is the input that you're giving, and that's the same for both cases. Okay, so this is for division, this is for addition and subtraction, and you see that the concept of error calculation that creeps in the final result is pretty much the same in both cases. Okay, and we should digress a bit when we talk about error in product, because we see that let's say if a into b is what we are trying to achieve as an input to find out the result, and we see that a has some error within it and b also has some error. In that case, what we need to consider is a fractional error between them. So let's say the maximum fractional error in x is delta x by x, and so that is obtained as delta a by a plus delta b by b. Okay, so the percentage error in the value of x, how much error creeps in, because of this is percentage error of a plus percentage error of b, right? So it's just a summation, and exactly the same is that for division, which is x equals to a by b. Maximum fractional error is delta x by x equals to plus minus delta a by a plus delta b by b, and percentage error in the value of x is equal to percentage error in a plus percentage error in b, and it is as simple as that, right? And that exactly follows the same concept as that of multiplication. So I give a question for you before I end the topic. Let's say I have x equals to a to the power m by b to the power n. What is the percentage error in value of x? And I leave this question as an exercise. Feel free to solve it. And I'll discuss the answer in the next class as usual. So we have come to the end of the topic, which is error analysis. We talked about significant figures, we talked about rounding off, and how we are trying to measure the values, error estimates, and how error propagates when we are giving something as an input. So that's the end of the topic, and until next time, see you in the next lecture.